Hello everybody, welcome back to my channel. In this video we're going to look at a problem called the set covering problem, or sometimes just referred to as a covering type of problem. And this is our third lecture in the series of integer programming problems. We're still going to be using those integer variables, in this case more specifically binary variables, to represent yes/no decisions in our problem. And in this particular case here, we will see that just like the knapsack problem, the covering problem has several different applications for it. So let's take a look at one example application, and then I'll tell you what other kinds of problems could fit a similar framework. Here's a story. There's this map over here, and it's subdivided. So imagine this could be the map of an area, an urban area, that was divided into neighborhoods. So I have 13, they're all numbered here, 13 neighborhoods. And currently, maybe this is a new area being developed. Currently, these neighborhoods, neither of them has a fire station. And given a neighborhood, of course, we would like it to have, the protection of a fire station. In this case, we're going to say that if there is a fire station that is close enough to a neighborhood, we'll say that the neighborhood is covered by the fire station. And what does it mean to be close enough in this particular story? And the explanation is here. A given neighborhood is considered covered by a fire station if either there is a fire station in the neighborhood itself, or one of the neighboring neighborhoods, that is a neighborhood that shares a border with that neighborhood, has a fire station. So for example, for neighborhood 2 to be covered, I could either put a fire station in neighborhood 2, or if neighborhoods 1, 3, 7, or 6, if any of those had a fire station, that fire station would be close enough to neighborhood 2 in a way that we could consider, yes, neighborhood 2 is safe. If there's a fire there, there's enough time for a fire station, for the firemen to get to neighborhood 2. All right, so that's the idea. So our goal is the following. We would like to have all 13 neighborhoods covered by some fire station, but because opening fire stations costs money, we would like to open the fewest possible number of fire stations in order to cover everybody. Okay, that's the idea of the problem. Now, what other kinds of situations fall into this framework of covering? Well, you could consider, for example, an area where you have to alert people about incoming tornadoes, and in some places they install sirens, right? When a siren is installed, there is a radius within which you can hear the noise. So you could think of that radius inside which the noise is loud enough as the coverage area of a given siren, and you want to install the smallest number possible of sirens so that wherever you are in this particular area that is tornado prone, you would hear in case a tornado is coming. Another example could be cell phone coverage, right? You could be installing antennas, and the antenna has a reach of an area that it covers. And if I am a company like AT&T, I want to be able to say, I am covering this whole area because I have antennas in the right places, but of course I want to install the fewest number of antennas possible. You can think of a surveillance context in which you're installing cameras to cover an area. Another example is, if you think of Tesla and their supercharging stations, right? They want to place those stations in the appropriate locations so that they can say, well, wherever you find yourself with your car running low on battery, you will always be close enough to a supercharging station so that Tesla can claim that you can drive throughout the US without worrying about running out of juice in your battery, right? So all of these are examples of covering problems. And if you can solve one of them, if you can model and solve one of them, all of the others are very similar. So let's focus on the one we have in front of us. And if you think about it for a little bit, you realize that what you have here are yes/no decisions, because in every neighborhood you could open a fire station or not. So in terms of the math, we can create one X binary variable per neighborhood. So we're going to have 13 of them. And this is going to say it's equal to 1 if I open a station there, and it's equal to 0 if I don't, right? Great. And if you remember from the knapsack problem, if I want to minimize how many stations I open, well, I'm basically counting how many are yeses among my 13 X variables. Well, to count, you simply add the binary variable. So your objective function will be, summing all of the yes/no variables. That is counting how many are equal to 1 or equal to yes, and you want to minimize that. So open the fewest stations, and my x1 through 13 are as I explained to you. Now let's go back here before we go back to the constraints. What do the constraints need to do? They basically have to enforce that there is coverage, right? Because if I don't enforce coverage, opening no fire station is a feasible answer, and that minimizes how many you open, which is 0. So let's focus on a particular neighborhood. For example, neighborhood 1, right? What needs to happen for neighborhood 1 to be covered? Well, either there must be a station in neighborhood 1, or a station in neighborhood 2, or 1 in 3, or 1 in 4, or 1 in 5, right? So unless at least one of these 5 neighborhoods here, 1 through 5, unless at least one of them has a fire station, then neighborhood 1 will be in trouble, right? Unless at least one of them has a fire station, neighborhood 1 will be in trouble. So I need to enforce that among the 5 stations that are close enough to neighborhood 1, and these guys are by the map, 1, 2, 3, 4, 5. Among these 5 yes/no decisions, at least one has to be yes, right? And this will guarantee neighborhood 1 is covered. And now that you've understood this line of reasoning, you can just apply this line of reasoning to every one of the other 12 neighborhoods to come up with these 13 in total constraints. So let's do one more just to practice. Neighborhood 2. Which stations have to be open? At least one of them. For neighborhood 2 to be safe, well, it could be neighborhood 2 itself, or one of its neighbors, which are neighborhoods 1, 3, 7, and 6. So going back to the math, at least one among neighborhoods 1, 2, 3, 6, and 7, at least one needs to have a fire station so that neighborhood 2 is safe, right? And this is basically the rationale behind all of these formulas. Great. So at this point, we're ready to go to Solver and put this in Solver and find the answer. As we usually do in Solver, we like to type just a few formulas and ideally just copy them and finish quickly. And this is how I decided to do this layout here. And this might remind you of the employee scheduling example in which we had the variables for the work weeks, and we had these zeros and ones right below them. And here's the idea. I have here in row 2 the cells that will play the role of the x variables, right? And essentially below each of these, I'm going to indicate, well, if I open that neighborhood, that fire station, right? If I put a 1 here, a yes, who can this fire station in this neighborhood, in this case number 1, help? And looking at the map, right, you would see that, well, 1 could help 1 itself, 2, 3, 4, 5. And that's why it appears in 1, 1, 2, 3, 4, 5, the first 5 constraints, right? Another way to see this is basically come here to the math and see variable x1. If you go through all of these constraints, it either appears in the constraint with a number 1 in front of it, or it doesn't appear in a constraint, right? And you see the variable x1 will appear in the first 5 constraints, right? That's why I have this one here in the first 5 constraints. If you want to look at this block of zeros and ones in another fashion, you can think of it in a row-wise fashion, which is to say, well, in this first row 3 here, right? We could call this constraint the cover neighborhood 1 constraint, the count. So this is exactly what the math here is saying, the first one, right? And who is there? Well, x 1, 2, 3, 4, 5, right? So if I do a sum product between the row of variables, right? And let me dollarize this. And this row of zeros and ones, for this Excel model to be mimicking what the math is saying, what is being produced in this cell N3 has to match exactly what the left-hand side of the first constraint is, which is essentially, I need the first 5 x's to be there and the remaining x's not to be there. And if you look at what this is doing here in Excel, well, I have 1x1, 1x2, 1x3, 1x4, 1x5, and 0 times everybody else, so everybody else is being thrown out. So this formula here produced the left-hand side of the first constraint. Now, if I were to copy this down through all constraints, you will see that my choice of where I'm putting the zeros and ones was such that each of these formulas will produce exactly what I need. So for example, look at this one. The second one, what I need to happen there is I need the first 3 x's to appear. 1, 2, 3. 4, 5 should not be there. 6, 7 should be there. And everybody else besides, after x7 shouldn't be there. And here you are. I have 1s for the first 3, 0s for 4 and 5, 1 for the 6 and 7, and 0s for everybody else because I want to throw them away. Right? So by placing the zeros and ones here according to where I see zeros and ones in the math, it allows me to type a single sum product formula and copy it through to get all constraints. Great. Last but not least, if you recall from the math, the objective is simply the sum of all the x variables, so we just have to sum them here. Sum the 13 x's. And now we're ready to do solver. So let's go there. Data. And here we are. So we want the objective cell, right? N16 to be minimized. Open the fewest number of stations. The variables are these 13 gray ones. The constraints will be, I want to enforce coverage, so I take the left-hand sides of these 13 constraints from N3 to N15 greater than or equal to the ones, right? P3 through P15. And I also have to ensure that these are yes/no decisions, so I can select all 13 x variables and say they are binary by choosing bin. Always remember that we're dealing with linear optimization problems, so change this to linear, LP. And in the options, double check that I'm not ignoring integer constraints and I want the true optimal solution by accepting a 0 optimality percentage here. Okay, now we can solve this. And let's see what comes up. Okay, so the answer I got here was it's possible to do this by using 3 stations. And I am placing them in neighborhood 1, neighborhood 11, and neighborhood 13. Great. And if you go to the map, you'll see that this works, right? The 1 in 1 covers these 5. The 1 in 11 covers these over here. And the 1 in 13 covers the remaining 8, 9. That was it. Now, if you stare at this map for a little while, because it's a small map, you would realize that there are other places where you could put 3 stations that would also cover everybody, right? So this is not the single answer that uses 3 stations and covers everybody. And it could even be that in your computer, it produced another one. That's totally fine because these are alternative optimal solutions. Now, when I present this problem in class, I typically do a second level of analysis with it, which is this. Again, going back to what I keep saying, that we never solve these models only once. We solve them, gain insight, change something, solve them again, etc. If you stare at this solution for a second, you might be wondering, what is the meaning of the numbers in column N, right? Is there some managerial interpretation for them? And, well, their meaning is the following. It's how many stations are covering a given neighborhood. And this 1 means there's a single station that can help the people in neighborhood 1. This 2 means there are 2 stations that can help the people in neighborhood 11. And if I were living in neighborhood 11, 12, 13, I would kind of feel a little safer than the other people. For the reason that, well, there's some sort of a fail-safe here, right? If a fire breaks out, the firemen go there. What if a second fire starts and there's a second fire station that could help me, whereas these guys have only 1? So you could think of the numbers in column N as some measure of redundancy in the system, right? And ideally, the larger these numbers are, the more redundancy this whole system here has, and the better it is. So once you realize this, you might be thinking, you know what? Now that I know, because I solved it the first time, now that I know that 3 stations are enough, and there are many solutions that use 3 stations, could I ask Solver to find me the 3 locations that make the solution as redundant as possible, right? So you realize that now I have a secondary objective, right? It's not minimize stations because I know what the answer is there. It's 3. But what I want to maximize redundancy while only using 3 stations. So let's create an updated objective. Let me call this guy max redundancy, right? And we could define, because redundancy is kind of like ill-defined, we could define redundancy as the sum of these numbers. The higher this sum is, the more redundancy there is in my system. Currently, it's at 16. And I would also like to, of course, if I just tell Solver, hey, maximize redundancy and do nothing else, it's going to simply open all 13 stations. And I don't want that, of course. So I'm going to create one more constraint to say, by the way, right? By the way, I want the number of stations that you use, which is that sum of the binary axis, to be 3. And I only know that 3 is the right value because I solved the first version of the problem first. Now I'm going to make some slight modification to this model in Solver and do this. I want my objective to be the redundancy. I want to maximize it. And I want to limit the number of stations that we have to be 3. Right? And let's see what happens. So watch this value here. Currently at 16, and only 3 of the 13 neighborhoods have redundancy, right? Only 3 of the 13. If we solve that now, let's take a look at what happens to this number here, 16. It should go up, right? Now it went up to 20, and let's see how many neighborhoods have redundancy now. So 1, 2, 3, 4, 5, 6. So we managed to double the number of neighborhoods from 3 to 6 that now have redundancy, and we still only needed 3 stations, right? And these are the new locations, neighborhood 3, 8, and 11. Okay? So again, this is brings me back to that thing I keep repeating. These models are very useful because they help you gain insight into the situation you are facing and maybe help you think of questions that hadn't even crossed your mind because you hadn't thought of the problem in certain ways. So that's the usefulness of these kinds of models, and you can always play with them and change the data and discover interesting things about the situation you are facing. This is all I wanted to say about the set covering example. I hope this was helpful, and thank you for watching. I'll see you guys again in the next video. Bye bye.